Okay, guys, we are going to do this little warm up today, but before that, so we are on, this should say lesson 4, unit 3, lesson 4, asymptotes and point discontinuity. And so by the end of today's lesson, you know about special cases of rational functions that have slant asymptotes and ones that have holes. Before we do that, though, we're going to look at this example here. And so far, we have looked at reciprocal functions, which are ones that are 1 over an original function. So it could have been a reciprocal of a linear, reciprocal of a quadratic. Then we looked at linear over linear, so something like this, where we had a linear over linear, and we talked about some of the rules that correspond in terms of finding those key characteristics. And now I just want to look at one quick example, which is a linear over a quadratic. So we're going to go through this in a very similar manner, identifying the location of any vertical asymptotes, horizontal asymptotes, x and y, intercepts, domain and range, and then we're going to draw a sketch of this. So remember that vertical asymptotes still are they come from solutions of the denominator. We can never divide by 0. So the x values that are restricted, which will impact our domain, are the ones that would make the denominator equal 0. So right away, we're going to do the same thing and say, okay, for vertical asymptotes, we would like to know what x values make x squared minus x minus 6 equals 0. So to solve an equation, a quadratic equation, we have to factor it. And this is looking like a simple trinomial. So we're looking for two numbers that add to -1 and multiply to -6. So likely we're going to be dealing with 2 and 3. And we are going to have x minus 3 and x plus 2. Minus 3 plus 2 is -1. Minus 3 or -3 times positive 2 is -6. So the corresponding solutions, therefore, vertical asymptotes will occur at two locations now, at x is equal to -2 and x is equal to positive 3. Okay, so we're going to have two different vertical asymptotes, and just like in any of the other examples, we have to examine the behavior on either side of these asymptotes. So we need to look at what's happening on the left of -2, so we might say -2.1. What's happening on the right of -2, so we could say -1.9. And really, we're just looking for, is it positive or negative? We also have to examine what's happening on the left of positive 3. So we could say at positive 2.9. And on the right of positive 3, we could say positive 3.1. So I'm going to use a graphing calculator to help us, or we could also use the reason I'm going to do this is because I don't want to give the graph away, so we're just going to use Desmos Scientific Calculator, and I believe this should help us. Let's see, f at x is equal to x minus 1 over x minus 1 over x squared minus x minus 6. And I wonder then if we can say f at -2.1. Okay, so to the left of that first vertical asymptote, we are getting negative values. And then to the right, which is -1.9, we're getting positive values. So if we go back over here, to the left, we got a negative. And to the right, we got a positive. And then we want to sub in 2.9 and 3.1. So we go back over here, and we could say 2.9. So to the left of the second vertical asymptote, we're getting negative values. And to the right, we're getting positive. Okay, so negative and then positive. So this is negative and this is positive. So now what we could conclude, we could say, as x approaches -2 from the left, f at x is approaching negative infinity. As x approaches -2 from the right, f at x is approaching positive infinity. And also, as x approaches positive 3 from the left, f at x is approaching negative infinity, and as x approaches positive 3 from the right, f at x is approaching positive infinity. Okay, so we're going to need that when it comes time to do our sketch. And so far, all we've done is A. We've identified the location of vertical asymptotes and the behavior on either side. Okay, horizontal asymptotes. So in all of our lessons before this, we have said that if the degree of the numerator is less than the degree of the denominator, okay, so if the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. We've held that definition consistently, but I'm just going to write it here. So b, numerator is less than the denominator, therefore horizontal asymptote at y equals 0. However, note that it may, remember that horizontal asymptotes could be crossed. We haven't looked at an example yet. May be crossed. And the important thing is, and you'll see as we graph, that if we cross an asymptote, we can cross it, but it still is dictating the end behavior of the function. The function will still ride along the top or bottom of that asymptote once it's being crossed. Okay, so we've got A, we've got B, and we're going to have to take a look. And the way we can check if it's being crossed is we want to check if this function has any x-intercepts. If the horizontal asymptote is at on the x-axis at y equals 0, but this function has x-intercepts, then the asymptote is being crossed, okay? So let's check that right now. Let's check our x and y intercepts. So x-intercepts happen when we have a function value of 0. So if we set this whole thing equal to 0, okay, so we say x-intercepts are when f at x equals 0. So if we set it equal to 0, but also hopefully you remember, really all we need to do is find the solutions of the numerator. Because if we set this equal to 0, we multiply both sides by x squared minus x minus 6 to get that out of the denominator. But 0 times anything is just 0, and all we're left with is 0 equals x minus 1. So really what we need to do is just set the numerator equal to 0. Because remember, that's the only way to make a rational function have a value of 0, is for the top to be 0. 0 divided by anything is just 0. The bottom cannot be 0 because then now we have a vertical asymptote, we have an error. So 0 is equal to x minus 1, and we use opposite operations, add 1 to each side. So we end up with 1 equals x. So therefore, we have an x-intercept at x equals 1. So we have a horizontal asymptote, but we do cross that asymptote. And y-intercepts are at or when x equals 0. And remember what happens when we sub in 0 when we have variables. This becomes 0, this becomes 0, this becomes 0, and all we're left with is the quotient of the constants. So we're going to have a y-intercept at negative 1 over negative 6. Okay, so we could say at negative 1 over negative 6, which is just positive 1/6. We're going to have a y-intercept at. Okay, so we've got x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, and then domain and range is the last one we're just going to state. And so for this one, we are going to say that the domain of this function is x is an element of real numbers. And we do have 2 vertical asymptotes, so such that x cannot equal negative 2 and positive 3. X will never be those amounts or those values. Now the range, we can say y is an element of the real numbers such that, but actually y can be anything that we want, because we do have a horizontal asymptote at y equals 0, but it's being crossed. So y actually can equal 0, and so that means we have no restrictions on our range. Y is just an element of real numbers. All right, so we've got everything we need here to sketch this function, and I'm just going to pause this so that I can get a Cartesian quickly. All right, so now I've got a Cartesian here, and we'll start putting our information. So we have vertical asymptotes at negative 2 and negative 3. So I'm going to grab my tool for my vertical asymptote. So one at -2 and one at positive 3. I might have just said -3, but it's positive 3. So we've a vertical asymptote there and a vertical asymptote there. And we have a horizontal asymptote at y equals 0. Okay. Now, we also have the end behavior around both of these asymptotes. So I'm going to grab my marker, and as x approaches -2 from the left, the function is approaching -infinity. So on the left side of this asymptote, the function is down here. And on the right side of this asymptote, the function is up here. Okay. As x approaches positive 3 from the left, so on the left side of this asymptote, the function is approaching -infinity, so down here. And on the right side of this asymptote, the function is approaching positive infinity, so up here. So that's what we know. Now we have to figure out what else is going on in between here. So we have an x-intercept happening at x equals 1. So the function is actually crossing the x-axis here. We have a y-intercept at positive 1/6, which is, let's say, right about here. It's getting pretty close in there. And beyond that, we can make some assumptions. We could investigate the end behavior, but because we're on the bottom of this horizontal asymptote, we have to be coming up this way. And because there's no other x-intercepts, I know that my function's not going to cross my horizontal asymptote again and end up here. I know it's going to stay below that. So I'm going to actually just make this so I can get a little bit closer. So I know it's coming from down here, and it must be coming up and going this way. Okay. Now in between here, I have to go from here to down here, and I have to go through both those points. So I can make some assumptions that my function probably goes something like that. Guys, I think that was the best graphing I've ever done on here. And then same thing over here. My function has to be coming from up here. I jinxed myself. And it doesn't cross the horizontal asymptote again, so I know that it has to stay on top of that horizontal asymptote. So we're coming from here, and we're coming down, and then we're cutting across like this. Okay, and then we could check our work. So now we could go back over to, there's where I was getting our Cartesian, take this function, throw it into our graphing calculator, and take a look at what this looks like. And look at that, that is exactly what it looked like. It's a beautiful thing. Okay, so before we move on to the, or now we're going to move on to the lesson. We've looked at another unique example. This was linear over quadratic, where we actually crossed a horizontal asymptote. You know what, I'm actually going to end this video before we move on to the lesson, just because it's already 13 minutes. And so there is like I said, another unique example. It's different than what we've looked at. It's linear over quadratic, but everything that we've learned still applies. And when we go through those key characteristics, we're able to get an accurate graph. I'm going to end this video, and then I will start a new video for the lesson.